Hi. In our last lesson, we had a leisurely introduction to probability. We understood the terms used in the study of probability, terms like experiment, outcomes, sample space, and events. We also looked at many different examples of calculating probabilities. In this lesson, we take the study further. We study the intersection and union of events and see how different events interact with each other. We then move on to a very important concept, the concept of conditional probability. Conditional probability leads us directly to the understanding of independent and dependent events. As always, we strengthen our understanding with a variety of problems. But first, let's start with something we all have learnt in school: set theory. I have two sets, set A and set B. How do these two sets interact with each other? Everybody is familiar with the Venn diagram. This is set A, this is set B. Now, the number of elements in set A we shall denote by NA, and the number of elements in set B by NB. Note that this is the total number of elements in set A and set B. But there are some elements that are common to set A and B. Those are denoted by NA intersection B. A intersection B, of course, being the set of elements that are common to both A and B. The union of the two sets, denoted by A union B, is the set of all elements that belong to A or to B. Or we want to get a formula that will relate the number of elements in the union to the number in set A, set B, and the intersection. This formula is simple enough. The number of elements in the intersection is NA intersection B, and the number of elements in A totally is NA. So this set would be NA minus NA intersection B. This corresponds to the number of elements in the set A, but those which are not in the intersection, or in other words, the number of elements only in A. Similarly, the number of elements only in B would be NB minus NA intersection B. Now we have three disjoint sets to consider: the set of elements that belong only to A, the set of elements in the intersection, and the set of elements that belong only to B. Clearly, the union of the two sets is the sum of these three disjoint sets. So the number of elements in A union B is the number of elements NA minus NA intersection B plus NA intersection B plus NB minus NA intersection B, which works out to NA plus NB minus NA intersection B. A well-known formula. This says that the number of elements in the union of two sets is the number of elements in A plus the number of elements in B minus their intersection. Let's see what this has got to do with probability. Recall that an event is just a subset of the sample space being the set of all outcomes. So basically, sample spaces and events are just sets. And to calculate probability, we count the number of elements in these particular sets. Let's look at an example. The set S is the set of integers from 1 to 100. What is the probability that a number randomly selected from the set is divisible by 3? So we know that P divisible by 3 would be number of elements div by 3 over 100, the total number of integers being considered. How many integers between 1 and 100 are divisible by 3? Well, 3, 6, 9, all the way to 99. If you count that, that is 3, 6, 9, all the way to 99, which is, I'll simplify these numbers. I'll take out 3 common since each is divisible by 3. And I'll get 1, 2, 3, 33. So it's basically the first 33 multiples of 3. So there are 33 integers between 1 and 100 divisible by 3. And we have our probability 33 over 100. Similarly, what is the probability that a number is divisible by 5? So P div by 5 is the numbers 5, 10, all the way to 100, which will turn out to be 20 over 100. Now for the interesting question. What is the probability that a number is divisible by both 3 and 5? By 3 and 5. So this looks like the intersection of the first two sets. The intersection of the set a number divisible by 3 and the set a number divisible by 5. If a number is divisible by both 3 and 5, it must be divisible by its LCM, 15. So we are simply asking numbers divisible by 15. How many such numbers are there? 15, 30, all the way to 90. Again, I pull out 15, that's 1, 2, 6. So the first 6 multiples of 15 all lie between 1 and 100. So P divisible by 3 and 5 is equal to 6 over 100. And the last question. We want P div by 3 or by 5. This is the union of the two sets. We want those numbers that are either divisible by 3 or by 5. So they should lie either in the first set or in the second set. Let's count the numbers that are divisible either by 3 or by 5. How many are there in number? So we have NA union B is equal to NA plus NB minus NA intersection B. We know that NA was 33, NB was 20, and then A intersection B we just found out was 6. So this answer is 47. Therefore, the probability that it's divisible by 3 or 5 is equal to 47 over 100. So let's get a quick formula for the probability of the intersection and the union of events. We just saw how we used the formula for the number of elements in the intersection and the union of sets. So let's start with that formula. NA union B is equal to NA plus NB minus NA intersection B. If I divide both sides by the number of elements in the sample space, that is, say, n, then the left-hand side is just the probability of the event A intersection B, while the right-hand side can be rewritten as NA over N plus NB over N minus NA intersection B over N. And that turns out to be the probability of A plus the probability of B minus the probability of A intersection B. And we have that the probability of A union B mimics the formula for the cardinality of sets. The probability of A union B is the probability of A plus the probability of B minus the probability of the intersection. This is the most general formula for the interaction of two events. We shall now see how this interaction changes depending on some special properties of those events. Namely, if the events are independent at one extreme and mutually exclusive at the other extreme. A card is drawn from a standard pack of 52 cards. What is the probability that the card is a face card? So let's call the event F for face card. The face cards are King, Queen, and Jack. And there are 4 suits, so there are 12 face cards in all. So probability of a face card is 12 over 52. What is the probability that it is a red card? R red card. Well, there are 2 colors in a pack, black and red, and there are equal number of red and black. So there are 26 red cards. Probability of a red card is 26 over 52. Is both a face card and red. So we're asking for the intersection. Probability of F intersection R. So to calculate this, we need to calculate the number of cards that are both a face card and red. Well, out of the 12 face cards, 6 will be red and 6 will be black. So the number of cards that are both face and red is 6. And the probability is 6 out of 52. And finally, we come to the question of their union. What is the probability that the card is a face card or a red card? So we are asking the probability of P, F, union R, which we know by our formula is PF plus PR minus PF intersection R, which turns out to be 12 over 52 plus 26 over 52 minus 6 over 52, which is 32 over 52. A simple application of the formula for the union. Moving on. In a class of 30 students, there are 17 girls and 13 boys. 5 are A students and 3 of these students are girls. If a student is chosen at random, what is the probability of choosing a girl or an A student? So let's set up some notation. N is equal to 30. The set of girls has cardinality 17 and the set of boys has cardinality 13. So it should be NG is 17 and N boys is 13. 5 are A students. So among the A students, 3 are girls and 2 are boys. So N girl intersection A student is 3 and N boy intersection A student is 2. NA is given to be 5. What is the probability of choosing a girl or an A student? So we want to look at the event girl or A student, the event G union A. We want the probability of G union A. I know that PG union A is PG plus PA minus PG intersection A. What is PG? How many girls are there in the total class? There are 17 girls out of 30. What is PA? How many are A students? Well, 5 are A students. So 5 out of 30. What is PG intersection A? That is, how many of the girl students are A students? Or how many A students are girl students? Well, they've told us that 3 of these students are girls. So there are 3 girl students who are also A students. So PG intersection A is 3 out of 30. And we have our probability of the union, which is 19 over 30. Therefore, The probability of choosing either a girl or an A student is 19/30. Moving on. A city survey found that 47% of teenagers have a part-time job. The same survey found that 78% plan to attend college. So, number part-time is 47. Number college is 78. The total number being 100 because these are percents. If 10% neither have a part-time job nor plan to attend college. Okay, so we need to decode this phrase. Neither have a part-time job nor plan to attend college. So they are neither in the set PT nor are they in the set college. They're out of the set PT or college. They are the complement of the set PT union college. They neither want to attend college nor do they have a part-time job. And this number is 10%. So 10. So what does this tell me about the union of the sets PT and college? Therefore, it tells me that the number that have either a part-time job or attend college must be 90. The other 90% must have either a part-time job or must attend college. And the question is, what is the probability that a teenager chosen at random has a part-time job and plans to attend college? So we are asked for PT intersection college. We've been asked to find the probability that a student both has a part-time job and plans to attend college. Okay, let's set up our usual formula. PPT union college is PPT plus P college minus the intersection. Do we have enough information? Yeah, PPT union college is 90/100. PPT is 47/100. P college is 78/100. And what's left is PT intersection college. So some simple manipulation gives us PT intersection college will be 47 plus 78 minus 90, which is 35/100. So this question needs to be analyzed a bit more. We were asked for the intersection, we were given the individual sizes of the sets, and we had to figure out the union. Once we had the union, we could figure out the intersection. But they didn't give us the union directly. They gave us the complement of the union. They said that 10% neither have a part-time job nor plan to attend college, which was basically all those teenagers who were not in the union of PT union college. And that was 10%. So PT union college worked out to be 90%. And using that information, we could finish the question. Let's move on to examining some special cases of events. These are the mutually exclusive events. The term is quite self-explanatory. These are events which can't occur together. They are mutually exclusive. So let's look at a typical example. Let the experiment be selecting a positive integer between 1 and 20. I define event A to be obtaining an even number and event B to obtaining an odd number. Are the two events mutually exclusive? So, having done the experiment, for event A to occur, the number must be even. If event A has occurred, is there any chance that event B will occur? No, because the number is even, there's no way it can also be odd. So the two events are mutually exclusive. Both cannot occur at the same time. If the number is odd, it cannot be even, and if the number is even, it surely cannot be odd. So event A and B are mutually exclusive events. Experiment. Selecting a positive integer between 1 and 20. Event A, the number is a multiple of 2. Event B, the number is a multiple of 5. Are the two events mutually exclusive? What do you think? If the event A occurs, is there any possibility that event B also occurred? That is, do they have any outcome in common, which would cause both events to occur? So the outcomes in event A are clearly 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And the outcomes in event B are 5, 10, 15, 20. So is it possible to select a number which will cause both event A and event B to occur? Yes, there is. The numbers 10 or 20. If the number 10 or 20 is selected, then both events A and B occur. So they are not mutually exclusive. They do have something in common. So here's the formal definition of mutually exclusive events. Two events are mutually exclusive if they have no outcomes in common. A and B are mutually exclusive if A intersection B is 0. That means there are no outcomes in common. Or in other words, the probability of A intersection B is 0. So these are very special types of events which don't interact at all. They have no outcomes in common. If one event occurs, we can be sure the other event has not occurred. Let's put this in the formula for the union. PA union B in general is PA plus PB minus the intersection. In this case, the intersection is 0. So for mutually exclusive events and exclusively for mutually exclusive events, the formula reduces to PA union B is equal to PA plus PB. The probability of the union is the sum of their individual probabilities. We draw a card from a standard pack of 52 cards. The event A is drawing a queen. The event B is drawing an ace. Find the probability that you can draw a queen and an ace, and the probability that you can draw a queen or an ace. So PA, there are 4 queens out of 52. PB, there are 4 aces out of 52. What about A intersection B? Can a card be both a queen and an ace? Of course not. So A intersection B is the empty set, and PA intersection B is 0. We have established that events A and B are mutually exclusive. Both cannot occur in one drawing of a card. So it's the probability of the union. What's the probability that the card drawn is a queen or an ace? It's 4 over 52 plus 4 over 52 equal to 8 over 52. Simply put, there are 8 cards that are either a queen or an ace. Let's look at one more question. You randomly draw one ball out of a bag containing 3 red balls, 5 white balls, and 4 green balls. The two events are drawing a red ball and drawing a green ball. Find P of A union B. So, P of A, there are 3 red balls. Out of 5 plus 4 plus 3, that's 12 balls. So the chance of getting a red ball is 3 out of 12, or 1 by 4. Event B, drawing a green ball. There are 4 green balls out of 12. So the chance of drawing a green ball is 4 out of 12, or 1 by 3. We know that P of A union B is P of A plus P of B minus P of A intersection B. So we need P of A intersection B. Now, the two events, drawing a red ball and drawing a green ball, are clearly mutually exclusive. You cannot draw one ball and satisfy both events. The ball can either be red or white or green. It cannot be both red and green. So, clearly P of A intersection B is 0. The events are mutually exclusive. So we get our required result. P of A union B is 1/4 plus 1/3 minus 0, or 7/12. An easier way to do this question would obviously be, you want A or B, so you want either a red ball or a green ball. So just count the number of red and green balls. That's 3 plus 4, 7. So the chance of getting a red ball or a green ball is 7 out of 12 in one drawing from the bag. Let's come to the other very important notion, independence and dependence of events. Two events are considered independent if they do not affect each other's probabilities. And two events are considered dependent if they do affect each other's probabilities. Let me elaborate. I have a certain experiment and I perform that experiment to get a certain outcome. Now there are two events, A and B. Does the occurrence of event A affect the occurrence of event B? That is, given that we know that event A has happened, does it change the probabilities of event B? We have some a priori knowledge that event A has already occurred. Does this knowledge in any way change the probability of event B? Remember, they are events of the same experiment and have the same sample space. Let's look at a very typical example. A bag contains 3 red balls and 4 green balls. You randomly draw 2 balls out of the bag. Determine whether the following events are independent or dependent. The event of drawing a red ball and drawing a green ball, with the first ball being replaced before the second drawing. So let's write these events clearly. Event A is drawing red in the first drawing. And event B is drawing green in the second drawing. We have to check whether event A and event B are dependent or independent. Event A is drawing a red. So when you first draw a ball, event A could occur or not occur depending on what ball comes out. Then you place the ball back into the bag and again draw it. Does the first outcome affect the second outcome? That is, whether we got a red or a green in the first drawing, will it affect what we get in the second drawing? If so, then event B would be affected by event A. If not, event B would not be affected by event A. Clearly, when we put back the ball and draw again, we are back to status quo. The probability of event B happening is not affected by what happened in the first drawing at all. So it's not affected by whether or not event A occurred in the first drawing. So in this case, events A and B are independent. Let's look at option 2. The events of drawing a red ball and drawing a green ball, with the first ball not being replaced. So if the ball is replaced, then they are clearly independent. A does not affect B's chances. Let's look at case 2. We draw a ball, we do not replace it, and then we draw a second ball. The events are the same, drawing red in the first drawing and drawing green in the second drawing. In this case, do you think the chances of B are affected by what happens in the first drawing? Surely they are, because it will change the nature of the bag. If a red ball came out, then the number of green to red balls changes. If a green ball came out, then again it's different. So, depending on what came out in the first drawing, will affect the probability of the second drawing. So, in this case, the events are clearly dependent. So, not replaced. Dependent. Whether or not event A occurred, that is, whether or not we got a red ball or didn't, will of course affect what we get in the second drawing, which is in what probability we get a green ball. A does affect B. I'm sorry, in the first case it was A does not affect B. So here we have a classic example of independent and dependent events. If the two events do not affect each other's probability, then they are called independent. If they do affect each other's probabilities, they are called dependent.